Hey everyone, this is Adam Gilbert. Thank you for tuning in. This is a video discussion to accompany um, some of the lectures I give in a, a course on predictive analytics that I teach. So this will be part of a series. This is the first video discussion I'm posting. This one, the objective is largely to cover some terminology and explain some concepts by looking at real data. So again, this is a companion to the first notebook in my class called Chapter 1, an overview. It's designed to cover terminology. If you're in the class, you haven't really seen any Python yet. You've hopefully been exposed to Jupyter Notebook through a notebook 0 called My First Jupyter Notebook, but that really just was designed to get you into formatting a Jupyter Notebook, typing some text, and then running some simple calculations. So no real Python yet. You will encounter some code in this notebook. I'll explain it as we go along. I encourage you to kind of dig into the code, play around with it. I'll give you access to the notebook itself so you can mess around and change code and see what happens. But if you're looking at the code and not quite sure what's going on, please ask questions and know that we will be covering this code in detail later on in our course. So here we go. We're going to start with a toy data set. And really all that means is we're constructing a random data set. So there's no meaning behind this data set at all. It's random data generated by the computer. So in our first code block here, I'll tell you what we're doing. In the first 2 lines, we're importing some libraries called NumPy and Pandas, which extend Python's basic functionality. We'll get familiar with these 2 libraries in particular throughout our course. From there, we're going to generate some random data, random X data. So we're going to store this in an object called X. We're getting random uniform values from 0 to 100, and we're going to pull 10 of them. Once we have that, we're going to generate some related Y values. So we're building essentially a data set that we can have a scatter plot of. Those Y values are related to the X values via some function here, but we're going to add noise to that. So we're adding some noise coming from a normal distribution centered at 0 with a standard deviation of 500, and we're getting 10 noise values so that we match the number of X and Y values we have. So adding noise to each Y value. And then for the fun of it, let's also build a color variable, which is going to be, again, a randomly generated data. Each observation is going to be either red or blue. It's just going to be a coin flip to determine that, and we're going to get 10 of those as well. So we have 10 X values, 10 Y values, and 10 color values. Then we're going to use pandas to create something called a data frame using those X, Y, and color values. And it's important that we have the same number of each here. So I'm going to run this code block and generate our data frame. Our data frame is our first real piece of terminology in our course. We're going to be using data frames a lot. Here is a data frame. A data frame is simply like what you think of as an Excel spreadsheet, right? Single tab on an Excel spreadsheet. I have columns and I have rows. Each row here is an observation. Python by default adds index values. So observation 0 has an X coordinate of 92.8, a Y coordinate of 13,847.7, and its color is red. Observation 2, we can read similarly. So each row here corresponds to an observation or a record in our data set. Each column, so X, Y, and color, we'll often refer to as a feature or a variable in our data set. So each column is a feature. Through this notebook, let's label Y as our response variable. We'll talk about other options for response variables, but the response variable here is the thing that we want to predict. Then we have the other features available to us. We'll categorize those as predictor variables. So X and color are predictor variables with which we can use the information encoded in those columns to maybe predict Y. Just calling X and color predictor variables doesn't necessarily mean that they're useful in predicting Y, however. So they might be useful. We've got two features in this data set, two columns that are numerical variables. X and Y are both numerical. The column the column color, or the feature color, is a categorical variable. This serves to group observations into categories. Those categories here are red or blue. Since every row in this data set or data frame is an observation, and every column is a feature, and every single cell contains one measured value of one feature or one variable for one observation, we can call this data frame or data set tidy. Tidy data is basically data that's in a form convenient for plotting, analysis, and modeling. Most data that we grab from the real world is not tidy. We're going to have to do a lot of pre-processing to it to put it in a format like this one, where each row is an observation and each column is a variable or feature. But for the most part in our class, we'll stick to data that's relatively tidy. We will have to do some cleaning, but not a lot. Okay, most of the data sets though, like I said, that we'll work with in our course are tidy, but a lot of data out in the real world is untidy. I just want to give you an example of that. So here's some data on refugees reported from countries over time. We see that each row here corresponds to a country. And then we have a bunch of different columns. So country name, country code, the indicator name, indicator code, then a bunch of years. Now, the year 1960 is not a variable, just like the year 2006 is not a variable. I can't measure 2006 for Afghanistan. But what I can measure is the number of refugees departing Afghanistan in the year 2006. So in this data set, we shouldn't have a column for each year. We should have one column which identifies the year, and then another column next to that which identifies the number of refugees departing that country or territory. So this data set would need a lot of work before we could move forward with analysis. All right, enough with untidy data. Let's get back to our tidy data set with X, Y, and color, and let's plot our data. So here we are. We have the X coordinate along the horizontal axis, the Y coordinate along the vertical axis, and the points are colored according to their color feature. So we'll get back into this in a second, but a few things moving forward. So the type of task we could be looking at. If we choose Y as our response variable, which is what we've done so far, we identified Y as the response earlier, and then the other features or columns as predictor variables, so X and color being used as predictors for Y, then we have what's called a regression task. The reason this is regression is because we're trying to predict a numerical response variable. So Y is numerical. If we're trying to predict Y, we're in regression. If instead, for some reason, we wanted to predict color as our response variable, color is no longer numerical, it's red or blue. And so it's categorical. So if color is our response variable, then we're working on a classification task. Again, classification just means that we're trying to predict a category or a categorical response. Both of the tasks we're outlining above are referred to as supervised learning tasks. That's because I have in the first case, the regression case, I have a column in my data frame for the Y values. I know the answers. I know the Y values in each of those records. And in the classification case, I have a color column, and so I know which observations are red or blue. Because of this, the model can check its answers when it makes a prediction. And it can see how close or how far off the prediction was in terms of the regression task, or in terms of the classification task, whether the prediction was correct or incorrect. And then the model can adjust from there. The model or the response column kind of behaves like a teacher with an answer key, telling the model, maybe we can envision the model as a student, to go back and fix its answers or go back and study a little bit more. So these response columns supervise the learning process. If instead of making predictions about X, Y, or color, we simply wanted to understand how many clusters or how many groups of observations we had in our data set. Well, now maybe these 2 points up here are a group. Maybe these 4 points these 5 points here are a group. Maybe this blue point off to the left, if it is its own group, and then this red point and that blue point belong to another group. There's no group column in our data set, and so our model is not able to check its answers. This is an unsupervised learning task because the model can't adjust by checking how well or poorly it's performing. All right, so now let's talk a little bit about modeling. We're going to go back to our original declaration of a response variable, which is to have y be our response variable. As a reminder, that's a regression task because the y variable is numerical. And we're just going to use the single predictor x to predict the values of the response y. We're going to build models here using some functionality from NumPy that we won't use moving forward, so I'm not really going to talk about it. What we're most interested in here at this point is just the pictures that result from this code. So we won't talk through the code, but here are some pictures. We've got our data, that's the blue points in the background. So the x coordinate, again, along the horizontal axis, the y coordinate arranged vertically. And we have some red models here. And these are all candidate models for predicting the value of y using information encoded in the x feature or the x variable. And we can see the models perform differently. Clearly, model 1 is not performing as well as model 2 or model 3. And it looks like on this data, model 3 is definitely fitting these data points the best. It goes through nearly all of them exactly. But if we think about our goal in predictive analytics and predictive modeling, we don't care to predict data that already happened. We want to predict data from the future. And so we want to predict unknown responses. So let's see how well these models perform on new data. What we're going to do is generate brand new data using the same generating process as we had before. So I'm going to create these new values in X new. They're going to range from 0 to 100, just like before. They're going to be pulled randomly with a uniform distribution, meaning everything is equally likely. And we're going to pull 10 of them again. We're going to generate now 10 new y values. Those y values are related to the x value in the same way as they were before. And we're generating the same random noise attached to each of our observations. I've commented out the color column here because we're not using it. So that color variable is not going to be generated again. And we're going to collect all of the x coordinates and the y coordinates in this new data frame called data new, and we'll print it out. So here's our new data points. These are data points that are coming from the future. The model didn't know about them ahead of time. And so let's plot these new observations on top of our old observations and the models that we built. So these are the same models from before. We're not refitting them. They're the same pictures as earlier, just with green observations pasted on top. The green observations are the new data points that we generated. We can see again, model 1 is not performing well on the green data points. Model 2 is performing pretty well on those green data points. Model 3, where it was getting everything nearly exactly correct before, is now missing pretty badly on a few data points, especially like this one here we can see. It's totally missing. And so what we can say from here is that model 2 is actually doing the best when it doesn't know the answers ahead of time. And so let's start with a little bit more terminology. We can say that model 1 is underfit. It's not wiggly enough to capture the general trend between the X variable and the Y variable. Model 3 is too wiggly. We're going to say that's overfit. It's learned too much about those blue data points, and the model actually is trying to fit noise in the data. Noise by definition is unpredictable. And so that model, while it looked to be doing really well when it knew the answers ahead of time, is no longer performing well on data that it didn't already know about. And so model 2 is sort of like this Goldilocks model. It's not underfit, it's not overfit, it's a little bit just right. But how do we know ahead of time that model 2 is the model that's just right? Because we really don't want to put either model 1 or model 3 into production and have it make business decisions or inform business decisions, because those business decisions are potentially really bad ones. And so we don't want to wait for new data to come in. We'd like to know ahead of time. And so let's talk briefly about a strategy for model construction and assessment. Again, we don't want to wait until it's too late to decide that our model's performing poorly or performing well. We need some way to simulate future data. So really just some way to hide data from the model so that the model doesn't know it exists. For this reason, what we're going to do is we're going to take our original data set, all of the data that we have access to, and we're going to split it into some training data. This is data that the model will have access to and the model can learn from, and validation data. So validation data, we might split into just one validation set or two validation sets or more than two validation sets. And we'll see reasons for why we might do that later on in our course. But for now, let's just say we're going to split the data into training data that the model will know about and validation data that the model doesn't get to see. The only difference between this approach and the approach we used earlier in this notebook and video is that we're going to take all of the data that we have access to initially and split it before fitting the model rather than waiting for new data to come in. So let's start by generating a new data set. We're going to generate this with a brand new association between the X and Y variable. We're going to generate 100 data points now. So again, X's are chosen randomly from a uniform distribution. Everything is equally likely to be chosen. A low value of 0, a high value of 100. So that's going to be the range of values where X's are allowed to come from. And again, we're choosing 100 data points. We're going to generate the Y's to be associated with the X coordinates. We're generating 100 of those also. The mean of the noise here attached to those Y variable values, so bumping this up or down from the underlying pattern that we're trying to discover. So the average noise is 0 and the standard deviation in the noise is 75. So the bigger we make that noise, the further away the average data point can get from the trend that we're trying to model. And again, we'll collect these, the X list and the Y list into a data frame and check out what that looks like. So here we're looking at only the first 5 rows of the data set. We're not going to print out all 100. Rather than building our model using all of the available data, like we discussed a little bit ago, let's split this up into training and validation data, or training and test data. We're going to take the first 75 observations as training data and the last 25 as test data. And I'm going to ask you now, can you think of any scenarios where this would be a bad strategy? There definitely are many scenarios where this is a bad strategy, and we'll look at better methods later on in our course. But think about that for now. We're simply, again, just going to take the first 75 rows as training data. The remaining 25 rows will be test data, and we'll print out the training data. So here we can see that rows 0 through 74, 75 rows in total, belong to the training data set. Let's plot the training data and the models that we fit on the training data. And so we can see a lot more blue points here. That's because we have 75 training data points. And we've got 3 candidate models. So we've got a straight line model. We've got a model that's allowed to bend a little bit in model 2, and a model that's allowed to bend a little bit more in model 3. So we've got 3 models now, and we have all of this hidden data, those 25 data points, with which we can assess our model performance. So let's bring in those 25 hidden data points and see how the models do. So here we're plotting in the background, the faded blue data points are the training data. Those are the observations that the model knew about ahead of time. The red curve or line you see in each of the plots are the model. Again, they're the same model as we had up here. We didn't refit anything. And the green data points are the new data. This is what we're trying to determine. Does the model fit the new unknown validation data well? And perhaps now you're noticing, well, it's hard to tell. Maybe model 3 is not great. It's turning away from these data points, but I'm not sure whether model 1 or model 2 is best. So don't worry, we have mathematical tools that allow us to aggregate the model performance by thinking about training error and validation error. So the training error is just going to be a single metric, a quantity that we can compute that assesses how well the model performs on training data. How does the model do when it knows the answers ahead of time? And for validation error, same idea, a single value, which kind of quantifies how well the model performs when it doesn't know the answers ahead of time. We're interested in that latter one. We want models that do well on future data. So we're going to spend a lot of time discussing model assessment and different error metrics later on in our course. For now, let's just use something called the root mean squared error. This is a popular measure for model assessment, and it's similar to the standard deviation in prediction errors. And so what we'll do is we're going to compute training root mean squared error and validation root mean squared error for each of our models. So again, the training root mean squared error is the errors that the model makes when the model knows the responses ahead of time. So you'll see that for model 1, this is that straight line model. The average error, the root mean squared error here is about 67.5. And model 2, the slightly more wiggly model, has a better training root mean squared error. It's allowed to wiggle more. If it knows where those response values are, it can wiggle closer to them. And so the training root mean squared error drops to 65.5. And for model, this should be model 3. I'm just going to change that now. For model 3, and this should be model 2, model 3. Sorry for those typos. For model 3, the training root mean squared error drops even more, but this isn't that surprising because model 3 was allowed to be more wiggly. The more wiggly the model is, the closer it can get to the data points as long as it knows the answers ahead of time. What we're more interested in is the validation error. Remember, the validation error is the error on the error coming from predictions on observations where the model didn't have access to the answers ahead of time. And so if the model didn't know the answers ahead of time, this validation RMSE was around 83, much worse than the training RMSE. But that's to be expected because the model didn't know the answers here, where it did know the answers for the training data. So in general, validation error should be higher than training error, or at least we'll expect it to be higher. Now, as we move from the straight line model to the more wiggly model, so the slightly wiggly model, our validation error increases. That's a different effect than we had with the training data. And so now we're starting to see evidence that adding curvature doesn't actually improve performance, it makes it worse. This is overfitting. And when we move to the very wiggly model, model 3, the validation error becomes even worse. And so here we're able to discover, without waiting for brand new data to come in at all, that when the model doesn't know the answers ahead of time, model 1 is actually the model that performs the best. All right, that's it for an overview. Again, this was mostly about terminology. Hopefully you have some big picture idea, some high level idea of the types of things we'll be doing in this course after watching this video. Again, I hope you found it helpful. Let me know what follow-up questions you have. I'm happy to answer them. Thanks, everyone. Talk to you soon.